I audible, students?
Yes,
Yes,
ma'am.
ma'am. Yes.
Okay. Students, junction DI characteristic are completed, and up to this it is what it was your syllabus. Today I'll move with junction breakdown. Junction breakdown, you most probably notice this point whenever you study VI characteristic curve in your lab. The PN junction diode current is very small before breakdown. This is the breakdown voltage. After that, the current increases drastically. The junction breakdown is that phenomena where current increases rapidly after a certain voltage. Two breakdown mechanisms involved here. One is called avalanche, and second one is called Zener. There are two breakdown mechanisms which leads to junction breakdown. The junction breakdown is that particular stage where current increases very drastically. You can consider this current, this is very, very small. This current is a drift current, which is observed under reverse bias due to the movement of the minority carrier. I discussed this section in your earlier classes. Now the question is, why after a particular point, particular voltage rather, the current increases drastically or very rapidly? Before discussing further, before discussing these two breakdown mechanism, I wanted to inform you here. Generally, for silicon diode, the critical breakdown voltage we observe at 60 volt above for silicon diode. It may be varied and it will be decided during the manufacturing time, because the doping concentration of the PN junction is absolutely matter, which will decide what type of breakdown we will observe. You normally know this PN junction will be reverse biased, and during reverse bias we observe breakdown after a critical voltage. First, I wanted to discuss the second one, which is the Zener, and then I'll move to the avalanche. I consider these PN junction schematics where I apply reverse bias voltage. This Zener breakdown mechanism is observed, or it is dominant whenever the doping concentration is large. That means for a heavily doped PN junction, we observe Zener breakdown. Why this is different? Student, you are aware with this equation. I mean, you are familiar with this equation that NaXP is equal to XPO. I write there NaXPO because it is under equilibrium. It is under equilibrium. That's why I write XPO. Right now it is under non-equilibrium because we are applying here reverse bias voltage. So I'll write here NaXP is equal to NdXn. XP and Xn are the extension of the depletion region width on the p sides of the junction. This is XP and this one is Xn. If you see this from this equation, it is very much clear that NdXn by Na is XP. Now, if Na is large, then XP will be small. Same concept is valid for the inside of the region, because Xn is equal to NaXP by Nd. So if Nd is large, then Xn will be small. Here I consider heavily doped PN junction. That means it is very much clear that under reverse bias, the width of the depletion region will not be wide, thin, it's not thick, it's thin. Thin depletion region will be observed under reverse bias for that type of for heavily doped PN junction. Now, what will happen, students? If we increase the reverse bias voltage, then more number of fill state will be in the opposite position to the empty state. And due to the thin barrier, tunneling of the carrier will occur, and at a particular high reverse bias voltage, there is a maximum flow of the current from the P side to the N side. By giving you the information, you are not being able to discuss that how this is possible, students. So for that one, I will mainly focus with the energy band diagram, because I told you the device engineer will be able to explain anything if they clearly demonstrate the energy band diagram. So energy band diagram is very, very important, student. Before doing the energy band diagram, please provide your attention here. We are connecting the battery in that way. Positive potential is connected to the inside of the junction. In the inside of the junction, electron is the majority carrier. By applying the positive potential to the inside of the junction, electron energy reduces. Positive potential is applied to the electron. Electron carry negative charge. Electron energy reduces. The same concept is validated also for the P side of the network. In the P side, we apply negative potential of the battery. In the P sides of the junctions, hole are the majority carrier. Whole majority carrier, whole carry positive charge, whole majority carrier, whole carry positive charge. You are applying negative potential of the battery to the P side. That means whole energy reduces. Students, ask yourself previously what I discussed. I discussed electron energy increases in the upward direction. Electron energy increases in the upward direction. Don't forget this point, student. Even this is valid for lateral also. Electron energy increases in the downward direction. That means if I consider some state here and some state here, two electrons here, this electron has a much higher energy compared to this electron. You absolutely know this point because you know this conduction band electron has a much higher energy compared to the valence band electron. You know this. Electron energy increases in the upward direction, so electron energy reduces in the downward direction. Electron energy increases in the upward direction, opposite is hole. So hole energy increases in the downward direction. We'll apply this concept due to the reverse bias connection. Electron energy on the insides of the junction decreases. So the Fermi level will move downward. Similar to that one, in the P sides of the junction, due to the application of the negative potential of the battery, the whole energy reduces, whole energy increases in the downward direction, whole energy will reduce in the upward direction, right? So I will draw the two Fermi level, I2, because here this PN junction is no longer in equilibrium. This under non-equilibrium. Under non-equilibrium, a constant Fermi level will not exist. The Fermi level is separated. Quasi-Fermi level will exist. Quasi-Fermi level for electron, quasi-Fermi level for holes. So EFP will be at the higher position compared to EFN. So I'll draw first two Fermi levels. First is EFN, because electron energy is reduced, and I'll draw a EFP here. See, right now the position of EFP is above than EFN. Why? I again wanted to inform you, pay attention to the energy band diagram, student. schematic diagram where I apply reverse bias. Positive potential is connected to the inside of the junction. Due to this connection in the inside, electron energy will be reduced. Electron energy increases in the upward direction. Electron energy will reduce in the downward direction. How you can indicate this? The energy band diagram by moving the Fermi level in the downward direction. That's why EFN is at the much lower position. You apply already in the P side negative potential of the battery, which is the reverse connection. Due to that one, the whole energy used energy increases in the downward direction, whole energy reduced in the upward direction. So we will move the Fermi level of the P side in the upward direction. So for this reason, EFP is above their EFN. Next step is what students you need to draw the conduction band and valence band. It is absolutely matter. This is because inside, right side is inside, so conduction band will be closer to Fermi level. You know that. And valence band will be away from Fermi level, inside. In the P side, Fermi level will be closer to valence band and Fermi level is away from the conduction band. So this will be somewhere. I try to consider equal energy band gap. That's why EC and EV gapping try to maintain 6. Now, what I will do, the two conduction band I will connect. This barrier is VO plus VR. You know this, students. I already explained this. Q VO plus VR. Sometimes I write Q VBR plus VR. That is absolutely same. Look at the situation right now. There is a very large potential barrier we observe here. You can see this gap. But here another point is important. Point is that thin barrier. See that? The barrier is absolutely thin. See? Look at this point. This is small. The thin barrier, the width thin. Why? I already explained this. This is due to heavy doping, heavily doped PN junction. So absolutely due to the heavy doping, still we apply reverse bias. We observe thin depletion region. This is the first point. Second point is go back to the concept of Fermi level, regular as well as transverse. Lateral you don't know, but I'll explain this in your extra classes. Right now, remember this point. All of the states below Fermi level are occupied by the electron. Now, if you pay attention on the p sides, these states are occupied by the electron. So these are the field states. All of the states below Fermi level are occupied by the electron. This is absolutely valid for p as well as for n. So in this inside, these states are filled, whereas these states are empty. All of the states above Fermi level are empty of electrons. So this is the empty states. So now what is the situation? Situation is that, take a look, filled states and the empty states are at the same energy level. See that I here draw a yellow line which indicates that filled state. Filled means the energy state is occupied by the electron. That's why I said filled. Filled states and empty states lie at the same energy level. First observation. Second observation is there is a thin barrier. Thin barrier. So whenever there is a thin barrier and the two field states and state are facing each other, then tunneling will occur. Tunneling. Tunneling of the carrier will occur. For the tunneling, these two conditions must be satisfied. The two conditions, I wanted to repeat it again. Note this point. Filled state and empty state must lie at the same position. That means they're facing each other. And there is thin barrier, narrow depletion region will exist across the junction. If this condition is satisfied, then what will happen? Electron will move, electron will tunnel from the filled state to the empty state at the same energy level. So what will happen, students? Because of this thin depletion region, electron from the filled state will move to the empty state. The electrons are moving from the valence band on the p side to the conduction band on the n side. This is the electron, this is the conduction band on the n side, and tunneling occur. You will be confused, the electrons are moving. Yes, but it is not moving from the conduction band to the conduction band. Movement can be in any energy state, but here we are observing electrons are moving from the filled state, that means on the from the valence band on the p side to the conduction band on the n side. Tunneling occurs across the narrow depletion region and the current increases. Absolutely, it is clear. Absolutely, it will be clear if I give you an example. We are very comfortable to move at the same level. But if we wanted to move at a high altitude, like whenever we move to the mountain, we are very uncomfortable. We feel uncomfortable. Same thing, electron can move very, very easily at the same energy level by just overcoming a thin barrier. So absolutely due to this tunneling or tunneling leads to a large increase in the current. This process is called Zener breakdown. Now, if you increase the reverse bias voltage, then there are more number of field states opposite to the empty state, so more number of tunneling, so more current. This is the process of Zener breakdown, student. I here wanted to inform you one point which is very, very important, because if offline mode of examination is arranged, then most probably you will face that type of question. These are the very common questions which came. What is the difference between the Zener breakdown and avalanche breakdown? The question may be asked during your lab viva, student, because you already work with the Zener diode in your laboratory, ECE391, called Electronic Device Lab. Know the basic, student. What is the difference between the Zener breakdown and avalanche breakdown? I'll not mention any point right now for avalanche. I'm mentioning one point here for Zener. Zener breakdown voltage, I'm writing this, decreases with temperature. Can you explain why? Okay, students, you must think, okay, these are the thought-provoking question. The question may be asked during your sessional exam. First of all, ask yourself this question, students. Whenever electron move from the valence band on the p side to the conduction band on the inside at the same energy level, they only need to overcome this thin barrier, and for that one they require extra energy. This energy will be absorbed from the applied electric field, because you know that under reverse bias two electric fields are present there. One is the built-in field and second one is the applied electric field, and both are in the same direction. That's why whatever the field that existed here, this is very strong, and those electrons will absorb energy from that applied field. Right now, whenever we increase temperature, if temperature increases, another form of excitation is given to the diode. This is in the form of thermal energy. Electrons, they will also absorb the energy from the temperature. So right now, electron will get sufficient energy considering thermal as well as at a much smaller voltage. It will be more confusing. I'll clarify you by considering example. Suppose I wanted to accrue 10 rupees per day. So if I consider there's a source of income from one point from which I will get 10 rupees, then I need to give more effort on that particular source of income compared to if I consider there is another one source of income. Under such a case, get 10 rupees per day, there's a less effort on that one source of income, because from the another source of income I can get more rupee. Like that, student, this electron needed to overcome only this barrier, thin barrier. So right now two form of energy is present there. One is from the electric field and second one is temperature. So at a much lower voltage, electron will accrue sufficient energy so that they can overcome this thin barrier and they can reach here. Reach here means on the conduction band on the of the inside. That's why I mentioned this statement. Zener breakdown voltage decreases with temperature. This is a very important point, student. You can include this in your difference note. Also, sometimes Viva or provoking question is out. That's why I mentioned this. Here, one point I wanted to mention, that due to the breakdown, current increases drastically. Yes, that is true, but it will not be destructive until the maximum rated current will not exceed the limiting value. This Zener breakdown mechanism is adopted for the construction of Zener diode. Zener diode is a specially designed diode which work in the breakdown region. This is Zener diode. If the reverse bias voltage exceeds the breakdown voltage, then the voltage across the Zener remain constant and the current increases drastically. The generator will work normally as long as the current will not exceed the maximum rated value, and the maximum rated value will be provided by the manufacturer in the data sheet. The value of the reverse bias voltage where the breakdown occurs can be controlled by amount of doping, because if doping decreases, then the width of the depletion region will increase. That means there will be more Zener voltage. So I will write a heavily doped junction. Heavily doped junction has a low Zener breakdown voltage. If we consider light doping, then high Zener breakdown voltage required. I'm not writing this. By knowing this point, the opposite one you can extend. Light doping means higher breakdown voltage. Here, one point I wanted to mention here. Generally, above than 80 volt, we consider predominant mechanism of breakdown is avalanche. Above than 18 volt, predominant mechanism of breakdown is avalanche. So below 8 volt generally we consider Zener breakdown happen. Zener diode is used for the design of regulator circuit. If you pay attention to the Zener diode characteristic curve, the Zener diode characteristic curve on the forward bias is same like ordinary diode. Zener diode operates in the reverse bias region. After down voltage, Zener diode normally work. Zener diode work in this region, where after a certain voltage, which we normally call VZ, Zener breakdown voltage, the current increases rapidly, but fixing the voltage on that value. The power dissipation of the Zener diode will be equal to VZ in the IZ. You know that V P is equal to V into I. So whatever the power dissipation of a Zener diode, we'll observe it needed to be taken carefully during the design of Zener diode, because rated maximum current is matter, because after breakdown VZ is constant. Which one increases? IZ increases. IZ max is the limiting factor during the power supply design, because whenever we design power supply, regulators are utilized. Why regulator is required? Students, you mobile charger, whenever you wanted to provide charge to the mobile battery requires DC supply, whereas in our home, the main supply is AC. So there is a requirement to convert AC to DC. For that purpose, ordinary diode in the rectifier mode is utilized, which convert AC to DC. After the rectifier, whatever the output we obtain, this is not pure DC. Pure DC is just a straight line. There will be no fluctuation. In this form of wave, we observe some types, some fluctuation is there. These are the ripples that needed to be overcome. For that, one filter is utilized. So in the power supply, by observing this format, there is no requirement of regulator. But I will explain you where regulator is required. In your home, sometimes, not every day, but sometimes you observe there's a low voltage or there's a high voltage. This actually happens to them due to the malfunctioning of some of the components which is utilized during the design of the power distribution circuit. Now, whenever this surge voltage is present there in the mains, it is very high voltage, which is present for long or generally short duration of time. This is a dangerous for the electronic component because those electronic components will work normally under a rated current and voltage value. And if this high voltage will exceed the maximum rated value, then whatever the electronic system like AC or refrigerator or TV we utilize in our homes or in our daily lives, they may be damaged. Some of the components may be damaged. We don't want this. We want it to provide a constant supply. For that one, Zener diode is utilized considering regulator. Regulator will regulate the supply. If the surge or high voltage or the fluctuation voltage more than Zener breakdown voltage, then diode will break down, and whatever the current that is being passed by the Zener, that will not go to the load. So that is not, which is harmful actually for the load. The load will be in the safe operating condition by turning on the Zener, that is break down the rest of the current being bypassed via Zener, and due to which the load remains safe. Load means I'm considering the AC or the refrigerator or the TV. Only a maximum, only a rated value will be passed by the load. Rest of the other current which is present there in the circuit due to the Zener breakdown, they are being bypassed by the Zener, and Zener will work normally. That is the design. That is why we utilize regulator in the power supply design. But students, here I wanted to mention that whenever you design power supply, oh, I write this. This VZ and IZ is very, very important. VZ is constant. We are not being able to do anything. IZ maximum is the limiting factor in the power supply design. This is all about Zener. Zener diode symbol, you know. This is the ordinary diode. And this is the Zener diode. Z. Next, let's move on with the avalanche. Avalanche breakdown is predominant for moderately doped or lightly doped p-n junction. It is also observed whenever the diode is in reverse bias. What will happen? Consider light doped p-n junctions. What is the difference in between earlier one? Here also we'll apply reverse bias, so same negative potential to p side, positive potential to n side. But due to the light doping, the width depletion region vary. The width of the depletion region vary. Here, wide depletion region will observe same concept, NAXP is equal to NDXN. So if light doping, then the width of the depletion region will be wide. So I think there is no issue. Remember this equation, student. Absolutely, it will be easy for you to explain these situations. Whenever n is small, x is large, same concept is valid for the other side. Now, whenever there is a wide depletion region is present, what are the changes from the earlier section we observe here? First is there is a huge amount of electric field is present there. Why? Because of this built-in electric field as well as applied reverse bias. Both are existing here, both existed here in the same direction. What you know, student, in the depletion region, electrons and holes will be generated due to the thermal agitation because this PN junction is no longer at 0 Kelvin. So some electrons and holes are generated there within the depletion region, and those electrons and hole pair will be accelerated by the applied reverse bias voltage or by the applied electric field. Electron will move in that direction, and this electron is at a higher velocity because of the absorptions of the energy from the high electric field across the junction. Whenever this highly energetic electron collide with the silicon atom, then what will happen? This highly excited electron release the energy. This released energy will be absorbed by the electron which is in the covalent bond within the silicon atom. Electrons agitated, they break the covalent bond. So covalent bond broken here. Due to the breaking of covalent bond, electron and hole will be created. So one electron, one hole. And this electron here comes by releasing the energy. Now these electrons move in these directions, and this hole will move in that direction. I think there's no need to explain why. Because of the electric field direction. See that electric field direction? This side is positive, this side is negative. Hole carry positive charge, so it will move towards P. Electron carry negative charge, it will move towards N. Now those electrons will also acquire sufficient energy from the applied electric field or from the electric field. So they are also in the excited state. During their movement, they will also make the collision with the other silicon atoms, creating more electron pair. This process is a continuous process, and due to which more and more electrons and holes will be generated. I already in your theoretical class discussed this section by considering impact ionization process. This is a one form of generation process, student. Thermal generation, phonon generation, and impact ionization. These three processes I discussed during the generation. You remember? Recombination process also I discussed similarly, software readable recombination as well as order recombination. I think you remember those sections. This is impact ionization generation process where due to the collisions, more and more electrons and holes are generated. It's a continuous process. We are not being able to control this. And due to the massive generations of carrier, there is a drastic increase in the current we observe. Okay, this breakdown voltage is called, this breakdown mechanism is called avalanche breakdown, and we observe this avalanche breakdown in a moderately or lightly doped PN junction. Now, students, by observing this mechanism of impact ionization, it will not be clear until I draw the energy band diagram. So let's move on to the energy band diagram. Please provide your attention here again. We are applying reverse bias here. Positive potential, the N side, so electron energy reduces. EFN will move downward. And in the P side, we are applying negative potential of the battery, so whole energy decreases. That means EFT will move upward. So like this case, I'll draw EFT above than EFN. So what is the difference here? I'll show you. So I'll first draw EFP and EFN here, like what I did for the earlier breakdown mechanism Zener. But here's some differences there. Let's do the modification here. This is the conduction band. Inside is the valence band. Fermi level in the P side will be closer to valence band. So this is EV and this is EC. As I already mentioned, student, this is likely PN junction. So there is a wider depletion region is present. See that wide depletion region, student. This is wide compared to earlier one, the blue. Also in this case, the barrier potential is same. I mean applied reverse bias plus contact potential QU plus VR. But from the earlier situation, the difference is here. The wider depletion region is present. So here, as because of field state is opposite to the empty state, this criteria fulfilled, but because of the thicker depletion region, the tunneling possibility is not existed here. So tunneling current is absolutely not present here. So what will happen here? Let's move on. So if you just take a careful look about this band diagram, it will be clear how the ionization will be observed. Due to the applied electric field, electron will move at a much higher velocity. So what will happen? This electron, which is at the conduction band, free electron, which is moving at a much higher velocity. In which direction? Towards N. Pay attention again here. Electrons are moving in the inside, toward the inside, student. Remember this point every time I cannot show you. This electron is moving in that direction. During their movement, they acquire sufficient amount of energy and they will break the covalent bond. Due to that one, electron is created and hole is created here. These holes will move in that direction, right? This electron will move in that direction. This extra electron which release the energy also is present here. Okay. So this highly energetic electron which move through the depletion region dislodge the electrons and holes due to the breaking of covalent bond, and due to that one there is a creation of more electrons and holes. I am showing you here only one breaking of covalent bond, but this is a long distance, and during this movement more and more electrons and holes pairs is generated, and there's a rapid rise in current we observe. If you pay attention to the movement of electron here, it will be clear that students, in this process, we are not following the mechanism which we follow for Zener. Zener, see that again, Zener, same energy level movement we observe. This one student. But here the electron absolutely move from the higher energy level, where electron is at the higher energy state. Electron energy is higher in the upward positions. The electron with high energy wanted to move, they will collide with the silicon atom by breaking the covalent bond. They liberate the energy and they come in the lower energy state. This is the lower energy position, students. They also dislodge electron hole pair. These electrons and holes are subjected to the electric field. They will move And following the same process, they dislodge the electrons and holes. So due to this avalanche, due to this process, there is a surge of electron, which is called avalanche, and this mechanism is called avalanche breakdown, student, which occur due to the impact ionization. Remember one point here. In your last section, I mentioned one point, this point, Zener breakdown voltage decreases with temperature. That means if we increase temperature, then Zener breakdown voltage decreases. But here in the avalanche case, you will observe avalanche breakdown voltage increases with temperature. Avalanche breakdown voltage increases with temperature. Next question. Just giving the statement, I cannot validate this. What is it? Why? Why this happen? Can anyone explain this? From your side, if anyone explain this, then try to explain. Okay. Think about that temperature. Temperature increases, students. What do you know? Temperature increases means probability of collision increases. Probability of collision increases means mean free time, tau, decreases. If temperature increases, mean free time decreases. You know this point. I discussed this previously during the scattering. Lateral, remember this point. If temperature increases, mean free time decreases. Now the next question is, what is mean free time? Lateral don't know. So for them, I am only discussing this. Regular know this. Mean free time is the time for which the carrier will exist in the structure. That means before the collision, what is the time that the carrier has in their hand using which they can move easily, freely? That is the mean free time. Now think about that. What is happening here? Electron, their motions is random. If temperature increases, then there is a more excitation because of the thermal energy. So there is a more probability of collision. That means whenever electron try to be in the direction, after some time, due to some other electron movement, the collision probability is increasing. That means previously at a much lower temperature, how much distance they traverse before they collide, that is reduced. Due to this, what distance that needed to be traversed by those carriers so that they can generate current right now, with increased temperature, they traverse smaller distance. So to overcome this large depletion, large width or long length, you can consider this length, the depletion region width, more excitation must be provided. The excitation is provided by considering breakdown or voltage, reverse voltage. That means more voltage you need to provide. So I can conclude avalanche breakdown voltage will increase with increasing temperature. Another point I can conclude here, if you increase the doping, then avalanche breakdown voltage reduces. That is just earlier concept. Next, whatever the large current we observe during this avalanche breakdown, that can be modeled by considering avalanche amplification factor. The current under avalanche breakdown can be modeled considering this. This is the total current J. JSO is the reverse saturation current density. This is the reverse saturation total current. What is M? M is the avalanche amplification factor. M is equal to 1 divided by 1 minus VR divided by VVR to the power M. What is VR, student? These VR is the applied voltage. V here is the breakdown voltage. What is N? N is a constant whose value is material specific. It depends, vary between 3 and 5. By observing the equation, it is clear closer the value of VR to VVR will increase M. If M increases, then definitely total current will increase. Remember this point, student, this equation is only valid for the values of VR smaller than VBR. Okay, VR এর ভ্যালু VBR এর থেকে অল্প হলেই কম হলেই তবে ইকুয়েশনটা ভ্যালিড, বেশি হলে কিন্তু নয়। Okay, this equation is only valid for values of VR smaller than VBR. So this is all about two diode breakdown mechanism, avalanche breakdown and Zener breakdown. If you have any query, you can provide your query right now. Otherwise, I will go for attendance. Students, I think there is no problem from your side. Okay, let's move on with your attendance. Roll number 62.